Good morning, class. Hmm? Good morning, class.
Hi, miss.
All right, good. So today's Wednesday.
Hi, miss.
Good morning, Samaya. Wednesday. All right, so what is your assignment for today?
Question 5 on the linear programming worksheet, miss.
Okay, so who is ready to share with question 5? What was the complete instruction? I have so many instructions here. Let me see if I can find it. What was the complete instructions? Come talk quickly, class. Have
Is the
marking to give a
other person that were assigned the queen theory questions are supposed to complete them, and then we were supposed to start question 5 on the linear programming.
All right. No. Okay. Yes, I am. Okay, so that's when I need to pick up. All right. The persons who were assigned the queuing theory. How far were we on the question paper? Come, class. We need to move fast. How far were we on the paper? And I want to ask you a question. Good morning, Ken. But after we have gone through some work, remind me, I said I want to ask you a question about the exam paper. The exam paper that just went, the test paper, test 2. How far were we on the queuing paper? Now, if we don't answer, move on to something else, because we have been at this long enough. Come, let's talk. What were the questions that are outstanding on the queuing paper?
So I think
we were supposed to do number 10. The
Number
last one that was done was 9.
Who had 10? Is it Mark and Peterkin who had 10?
yes, and number
Yes,
6
miss.
wasn't done.
Giovanni Lawrence for question 6. Markland Peterkin for question 10. I have the homework written down here. Sometimes I'm not sure if it is what it is, but it is. Markland, question 6. Is Giovanni Lawrence here? All right, Markland, please go share your question 10.
Give yourself a hand.
It's not allowing me to share.
I'm sorry, I think I need to give you that capabilities. Give me a second there. All right, there, you should be able to do that now.
Now for our last activity, choose one of the following things or experience I'm going to be.
I see, miss.
Yes, yes, I'm seeing it.
Okay, so this is what I did for question 10, which is the Peachtree Airport in Atlanta serves light aircraft. It has a single runway and one air traffic controller to land planes. It takes an airplane 12 minutes to land and clear the runway. Planes arrive at the airport at the rate of 4 per hour. A, determine the average number of planes that will stack up waiting to land B, find the average time a plane must wait to inline before it can land. C, calculate the average time it takes a plane to clear the runway once it has been notified the airport that it is in the vicinity and wants to land. And D, the FAA has a rule that the air traffic controller can, on average, land planes a maximum of 45 minutes out of every hour. There must be 50 minutes of idle time available to relieve the tension. Will the airport have to hire an extra air traffic controller? Okay, so
Hmm.
this is what I did for the
Go
first
back
one.
up. Go back up a little bit for me. Go back up a little bit for me. Go back up to the. All right, stop right there. It takes an airplane just to make sure that you have the. Takes an airplane to take a single runway. 12 minutes to land and clear. Ah. So 12 minutes to land and plane arrive at the airport at the rate of 4 per hour. So 12 minutes to land. All right. So that's, go ahead now. Let me see what's your lambda and your mu.
Okay, so my lambda was actually divided the 4 by 60 because I had to put it down into minutes. So I got 0.6
Um,
and then I put it in.
Give me a second there. Let me double check something. I mean, I know what to say, but let me double check what you did. Uh, it was such a valiant attempt. I'm sorry I have to tell you that it is incorrect.
Okay. Where did I go wrong?
Go back up to the thing there. Right there. Back straight up to the right here. It says it takes an airplane 12 minutes to land and clear the runway. Right? So one airplane takes 12 minutes. So in the hour, you can clear 5 airplanes per hour. Good. So the service rate
Okay.
means the air traffic controller can land 5 planes per minute, right? And go back up,
Okay.
go back. And the plane arrives at the airport at the rate of 4 per hour. So while the air traffic controllers can land 5 in the hour, they arrive at 4 within the hour. So your lambda is 4 per hour on average, and your mu, that's your service rate, is 5 per hour. We see that?
Oh,
So come, we're
okay.
gonna work the question together now. So type, so your lambda, so just go below that, right before where the incorrect things, go to the last line and go. So L, right.
Okay.
Good. The question is asking you for the number of planes. What was the question asked you for again?
Um, the average number of planes that will stack up waiting to land.
So your LQ. So go down. So you were correctly identifying that it is asking you for LQ. So LQ now, so you're going to work the correct thing. Good. So LQ now is, thank you, Keon. Keon is showing that in the chat. It is lambda square. So that is 4 square, sorry, And mu now will be 5. So the service ratio is divided by 5 open bracket 5 minus 4. So that works out, close your brackets. So that works out to be 16 divided by 5. So it's actually 3.2 because 1/5 is 0.2. So 3.2 planes, right? Good. So
Okay.
it's 3.2 planes are lined up for. So if you get your lambda and your mu incorrect, it's grief because everything it turns out to be incorrect. All right.
Yes, miss.
All right. So that is how you. The second question now. The second question.
B.
What did B
What
ask
the
just
second
for?
question now? Find the average. Find the average time a plane must wait in line before it can land.
All right, so that's WQ. So when you go and you're up there circling the runway, or the pilot tells you that you're now approaching the runway, you can't just approach and just go boom and land. If there are other planes ahead of you and they're on schedule, they will have to line up just like you're in traffic on the ground. You line up one behind the other and you land on the available runways, the one that can accommodate the length, the size of your plane. So driving in the air, flying in the air is pretty much similar to um, driving on the road. You still have rules by which, and you have to fly in a certain flight path. So you can't, if you're supposed to be at 30,000 feet, you can't go down 25 because you're going to crash into somebody else. So the flight air traffic controllers are there to keep you in your lane. Make sure you stay on your flight path, right? Good. So the time waiting to land would be lambda over mu into mu minus lambda. So it would be 4.
So this would be the formula, or is it the?
No, I'm using the standalone, which is lambda over mu into mu minus lambda.
Oh, okay.
So it is
So
similar to the LQ, except that there is no square in the top. All right. So take out the LQ, just put lambda.
mhm.
Divided. So just copy and paste the denominator for the LQ.
Oh, sorry. So lambda
Mhm. Divided.
divided by
Whatever is in the denominator for LQ.
3.2.
No, go back up the formula. You see what is in the LQ?
Oh, this. Okay, okay.
All right.
I'll just copy this.
Mm-hmm. So take out the square now from the lambda. So take off the square of the lambda. There, you have the formula for WQ.
Lambda. Our.
This that you have in the
F.
line.
I know.
Right.
I'm just going to type it, though. I'm not going to copy it.
Mm-hmm. All right. We know that the mu means mu.
Yeah.
Good. There you go. So if you know one, you know the other. You just take off the square for the top and you're free to go rather than this whole heap of LQ divided by that and you're gone off to the corner to calculate this. Too complicated. So it would be 4 divided by 5 divided 5 open brackets, 5 minus 4. Oh, look. The brackets, you need to depress your shift key. Go back to where the 9 is and take out the 9. All right, so make sure you depress your shift key.
Okay, so 5.
Open bracket.
5 open bracket.
5 minus
5 minus
4.
4.
Yes.
Okay.
Close bracket. Good. So that is 4 over 5. So that is 0 0.8.
0.8.
8 of an hour. Or you can multiply that now by 60 to give you the time in minutes. 6848.
So multiply this by 60
Yes, to give you
to
the
get it
time
in hours.
in minutes. To get it in minutes.
Times 60
To get it in minutes.
equal
48 minutes. Yes.
So it's 48 minutes.
Yes, you have. It's not unreasonable. You have many situations if you follow. Just read the news, where you have instances where planes have to circle the airport, for however long, and you have one or two instances where some of them run out of fuel because the airfield is so congested. They have to wait their turn, and sometimes have accidents because of it. But that's the way it works. What was part C?
Actually, the average time it takes a plane to clear the runway once has been notified the airport that it is in the vicinity and wants to land.
Good.
So that would be W?
Yes, that would be W. We're not going to do the last part because it's a bit more complicated for this section.
I didn't do the last part either.
Yeah, it's a little bit more complicated than I had wanted it to be. So we will leave that part.
Okay, so that would be
W. Just put 1 over 5 minus 4. So W is 1 over mu minus lambda. That's the easy formula.
1 over
mu
5 minus 4.
Yeah, so take out that formula that you have over at the top. That's the easiest way to do W. 1 over mu minus lambda.
So it just would be 1?
Yeah, that means 1 hour. What does the 1 mean? 1 means 1 hour.
Okay.
Right, and so 1 hour are full 60 minutes. Or 60 minutes, yes, or 60 minutes. Yeah. So I use the simpler formulas. Good. So that is it for question 10. So Markland, when you get a question where the times for arrival and the times for the service rates are different, hold a minute. Sorry about that. My nephew taking shortcut when he's work, but he know what's going to happen. So him never do the experiment. But clap him, you see. All right. So, Markland, back to you. When you have, and to the rest of the class, when you remember, when you have the arrival rate and the service rate being in two different measurements of time, my advice to you is to convert the time that is in the smaller unit to a time that is in the bigger unit. David Gordon Rowe did a problem last week, but he converted this bigger unit to the smaller unit. My strong sense is that he got a little help to do that. Usually students don't do that well when they convert from the bigger unit to the smaller unit, because you end up having to do many decimals. And students don't like decimals as far as my sense of experience carries me. So it is usually better to go up to the bigger units. So it's like changing out your 1 cent coins for a single hard dollar rather than changing the dollar into 101 cents. Right? It's usually easier if you go up to the bigger unit of time. Good. So always remember that when you have two different units of time, it is better if you go up to the bigger units. However, if on your own you're very comfortable with decimals and reduction to a smaller unit, you should do that. But be very careful, right? You tend to make more errors, so you have to be a little bit more guarded if you're going to go the way that David went last week. All right, so I hope that was helpful, Markland.
Okay, thank you.
You're welcome. Good. So that's question 10. Who had, that was it? I only have up to question 10 allotted here. Was that it? No, you said we did.
Yes, so
All right, so question 6, Giovanni Lawrence is supposed to do question 6. Is Giovanni here? I have absence, no show. Means he wasn't here last week. Is Giovanni here? No. Has anyone done question 6 and would care to share it with the class?
I did it last week.
Okay, go right ahead. Who said they did it? I'm not seeing who is talking. Who just said you did it? Huh?
Tashik.
Tashik? Okay, Tashik. Very good. Go ahead, Tashik, and share with the class.
Okay.
Mhm.
So question 6 said, Avid Interior Design provides home and office decorating assistance to its customer. In normal operation, an average of 2.5 customers arrive each hour. One design consultant is available to answer customer questions and make product recommendations. The consultant can deal with 3 customers per hour. And the question said, compute the operating characteristics of the customer waiting line, assuming person arrival and exponential service time. So when the question said operating characteristics, so it was operating characteristics is the same thing as queuing characteristics. So we will find LQ, which is the number of units in the queue, and WQ, which is the time spent in the queue. So
Okay,
first,
sorry, hold on a minute. Tashi, give me that reason again. That operating characteristic is the same as Q characteristics or something of the sort? Go again.
yes, I said the queuing characteristics.
All right. Queuing characteristics, so let me correct something on the ground. When we talk about the operating characteristics and the queuing characteristics, yes, they're equivalent, but it is not 2. There are 6 queue characteristics, not 2. So the 6 Q or operating characteristics are the PW or the rho, which is the utilization rate. 2, the probability that the system is empty, that's P0. Then you have the average time waiting in the line, that's WQ. You have an average number waiting in the line, that's LQ. And then you have the system's time, which is W or WS. And you have the number of persons in the systems, which is L or LS. So there are 6 elements to a Q or the operating characteristics of the Q. All right, so please correct that. All right, good. All right, continue though.
Okay, Miss. So first I identified the lambda and the mu, which was lambda was 2.5 and mu was 3. And sorry, Miss. For LQ, it's lambda square over mu times mu minus lambda, which is represented here. And I got 4.16 customers. And WQ, which is represented by this formula, LQ over lambda, and I got 1.664 hours.
What is that 1.664 hours about? No, what is that 1.664 hours about? The wait time? How many how many minutes would that be? That looks like 104 minutes. What is 1.664 minutes? 1.664 hours. Multiply that by 60, please.
99.84.
Good grief. That's a whole lot of time that the person has to wait. 99.4 according to your decimals. You have how many decimal places? 3 decimals. Okay. 99. So right, or 99 point however minutes it work out to be.
Should I take out the hour, Miss?
No, you write or. So you write 1.66 hours or, so insert an or 99.8 minutes.
That's what I did for number 6, Miss.
All right, number 6. All right, so that's all you did for number 6. So, no, Tashik, put back your work on the board. Good. All right, so remember now, the correction to Tashik's work is that she needed to have done all of the 6 characteristics. So when we say operating characteristics, we are talking about all 6. Now, did anyone do question 6 and computed or derived all the characteristics for the question? No? All right. So it means that the rest of the class has those to do. Now, there was other part to this question, was not there? Is there another part to the question? Tashik, was there another part to the question? That's it?
No, Miss. Yes, only A.
Okay. So I don't know. Yeah, well, yeah, it would be A because that would be a lot of work to do. So you must do all of the 6 named characteristics if you're asked for the operating characteristics. Always remember that, please. All right, so would that take us to the end of the tutorial questions that were outstanding for the queuing? Come class. Okay, Ken. Thank you, Ken. Thank you. All right. All right, so question 5 on the linear programming worksheet. Did everyone do question 5 on the linear programming worksheet as asked? It means then I can ask anyone to share your work with me. So Shakilia.
Yes, miss.
I can. Please share your work on question 5 on the linear programming worksheet.
Yes, I'm not sure if it is correct. Yeah.
It's okay. That's not what we're asking for. We're asking for your attempt at it. So don't worry about that. If it needs to be corrected, then so will we correct it.
I didn't get the chance to type it up, miss. So I took pictures and then just paste them in the Word document.
That's fine. Lori, why didn't you do the work, Lori?
Yeah. I'm trying to find the question, miss, to open the document on me.
Okay. All right. Well, that's hence my wanting us to get to here this morning. We need to get to it. We will have to do selective questions, but we will do enough so that you are able to oh, let me look at something in inbox. Is that my inbox? No, that's not my inbox. Hmm.
Alright, so question 5 on the linear programming.
Mm-hmm.
So the question says, find the feasible solution points for the following constraints.
Mm-hmm.
The first one, A, is 4x1 plus 2x2 is less than 16. Now, what we have here is a statement, but we want to convert that into an equation so we can solve for the different variables, which is x1 and x2. So in order to do that, I just remove the less than sign and put the equal sign. So it now becomes 4x1 plus 2x2 equals 16. And to solve for the different variables, we have to equate each one to 0. So um, where x1 equals 0, I get 0 plus 2x2 equals 16, and then I just transpose to find x2, which would give me 8. And here I have it where x1 equals 0, x2 equals 8. And then I did the same thing for the second one. I equated x2 to 0, means it will be 4x1 plus 0 equals 16, transpose again, and got x1 to be 4. Here, where x2 equals 0, x1 equals 4. And for the graph, I just plot the points. So usually in the question, the first variable is the x variable, miss. Goes on the x-axis. So x1 would go on the x-axis, and then x2 goes on the y-axis, and then I just plot the point. So for x1, it would be 0 and 8, and then you'd have your point right there. And then for x2, it would be 0 and 4, and all you need to plot a line is just 2 points. So I just connect the dots, miss, and then here I have the equation. But the question says 4x1 plus 2x2 should be less than 16, which means you would shade to the left. So anything to the right would be infeasible, miss.
Mm-hmm.
And that's what I did. Yes, miss, that's for the A.
All right, give me 1 second. I'm just checking for something here. I'm trying to. August, July. Give me a second, please.
Yes, miss.
That's not what I want. Let me close that one. I'm sorry, I'm searching for something. Let's double check on something. All right, give me a second. Uh, mm, 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 mm. All right. Okay, I figured out what I want. All right. So everyone didn't do question. So we're gonna do 2 questions. Someone display your tutorial sheet for me, please. The tutorial sheet. Thank you, Tashik. Display your tutorial sheet, not Tashik. Who did the work for me? Someone display your tutorial sheet. Thank you, Abigail. All right, scroll down for me. All right, stop there. All right, go back up. Stop right there. All right, thank you. You can take that down now. All right, so in the interest of helping those who do not understand, I am going to share my screen and I'm going to work that problem on the board because it is essential that you understand those basic elements before you can properly tackle a linear programming question. Now, for linear programming, you would have gathered from your lecture that linear programming is used whenever a decision maker has a resource that can be utilized for varying purposes. So it is only used in instances where you have a resource that you can use to do many different things. So for example, suppose you have some board or you have some bags of concrete. Well, let's use board. Suppose you have some boards, right? You went and you illegally maybe cut down the mahogany tree you shouldn't have cut down. So you have these lovely boards. What can you do? What can you do with those pieces of lovely boards? Someone from the class, give me one activity you can use the boards to do. Quickly, class.
Build furniture.
You can build furniture. What else can you use the board to do? Come on, class. Build furniture or what? If you don't speak, I'm going to abandon the effort to help you. Build furniture or what?
Make a bookshelf, miss.
All right, so in the furniture, you can use it to do many pieces of furniture. You can build bookshelves. What else can you use it to do in building furniture? Bookshelves
Bed.
or a bed.
Beds.
What else?
Chair.
Dresser.
Tables, chairs.
These are just some of the things. So from the activity of building furniture, you can use it in building many different kinds of furnitures. Well, no, sorry, there's no S on furniture. Building many different kind of furniture. You can build bookshelves, and if you walk into courts, you see bookshelves, you see bed frames, you see tables, you see chairs, you see dressers, all built from wood. So if you have wood, you can build many pieces of furniture with the same wood. The question now that confronts the furniture maker is, should I build all bookshelves? Or wait, it's Christmas coming, people want new beds. Should I use my wood to build beds instead? And he scratches his head and says, but people want their dining room to look good because they're going to invite over, well, 15 friends at maximum. So they want to have nice tables and chairs. So should I build some tables and should I build some chairs instead? And maybe you want to dress up your room. So maybe dressers. So the problem that faces a decision maker is, how on earth am I supposed to use a limited amount of wood or limited number of pieces of wood that I have and decide, should I make some of each of these 5 items? Should I make only 2 of these 5 items, 2 out of the categories of these 5 items, or should I make some of each of the categories of each item? So that's a real problem. And it's a problem because he has only so many pieces of wood. He doesn't have an unlimited number of pieces of wood. So a linear programming is what the decision maker will now use to decide how he should allocate his limited number of pieces of wood across these many different considered investment items that he can make. If the wood could only build bookshelves, then there's nothing to consider because, well, you can only use it to make bookshelves. So linear programming is only used when you have an resource that is in limited quantity, but that resource can be used to make many different items. The furniture maker can now phrase his objective this way. Since I have limited amount of woods or a limited number of pieces of woods, what am I to do? Do I want to make items that would give me maximum profit? Or do I want to make items in which I would incur the least waste of my wood? So he has 2 avenues that he can take to consider how he's to approach the problem. That is, he has 2 objectives that he must choose which one he's going to pursue. Is he going to build high-end items and get maximum profitability? Or is he an environmentalist where you want to build items and reduce waste or cost? So is he going to be maximizing profit or minimizing cost? Whichever objective he chooses, he must choose one. Say he's capitalist minded and he's going after profit. His objective then would be how many of each item to build such that he makes maximum profit. So he's figured out that he has this resource. He can make these number of items from the resource. The question is now, with what objective is he going to seek to produce these items? So maximizing profit or minimizing costs. He chooses to maximize profit. So you write down his objective to choose to maximize profit by building X number of beds, Y number of tables, Z number of chairs, P number of dressers, whatever. Or is he just going to choose to build between tables and chairs or beds and tables? Whatever elements he chooses to build, you know his objective is to build them so that he maximizes profits. Now, in building the beds and the tables, he needs the wood, but he doesn't just need wood. He needs qualified carpenters. He needs the time to allot to building the items. He needs the varnish. He needs the space with proper ventilation to operate. So he's going to be faced with certain required elements to carry out his or to seek to achieve his objective. He needs space, proper space with proper ventilation if you're going to use those chemicals like the varnish. So where is he going to get big enough space with proper ventilation at reasonable cost, within reasonable striking distance of his market? Right there, he's facing a limitation with his availability of space. Marcus Garvey Drive, way down in the country, where is he going to go? So he's faced with limitations. Now we have an embargo on getting things from China because of the virus. So he may be facing limitations in the accessibility of varnish. The varnish is his tables and his chairs, if that's what he's going to build, or his beds and tables. is also going to be facing a limitation on time. The Ministry of Labor says that you must work this is the number of hours you must work, and after that you have to pay double time, half time, 1.5 times. So it's also going to be faced with the time that the workers may be able to work. So right away, he wants to profit from building his beds and his tables. And he wants to make as much profit as he's able to. But right away, he's faced with limitations on his ability to make as much profit as he would like to do. We call these limitation constraints. So he has an objective, but the objective is subject to some constraints. So that is the nutshell of a linear programming problem. You have a resource or some resources that you can use to make alternative activities or elements or items. You decide what objective you're going to make these elements or items in mind with. That's an awkward sentence. What is the objective you're going to be using to make your items? But the objective, you can't achieve your objective infinitely. You can't just go willy-nilly. One, because the resources that you have are limited. Two, you're going to have other constraints that are going to prevent you from achieving your objective in an infinite manner. Then the question then is, what's the best way to proceed? In the light that you want to achieve this objective, you face this constraint, what then must you do to achieve your objective in the best possible way? So linear programming is the go-to tool to help in this time of questioning need. So what we do then is that you gather your information. And notice the name, linear programming. So you gather your information, you write them down. You need this amount of wood, or you have at most this amount of wood, or you need this at minimum length of wood. How many pieces does it take to make the legs of the bed or the tables, whatever it is? Or I don't know how to make stuff, but you have an idea what I mean. How many pieces of wood you're going to need to make the bed or the table? How many tins of varnish you're going to need to make the varnish on the table? How many hours of labor you're going to need to make one table and one chair? How many do you have in terms of the number of tins of varnish? How many hours your laborers can work, or your workers can work, your carpenters can work? How many pieces of wood do you have in storage to make all these very nice things that you want to make? And then you get to work. You can't solve the words. These are making things. These are quantity of things you want to make. So you have to ask yourself, how many of each should I make? And so you translate those ideas into equations or inequations. Inequations means that you have less than or more than in the expression. Equations have an equal sign and terms on both left and right. So the question is, if it's an inequation, suppose you need 2 pieces of wood to make chair and 3 pieces of wood to make a table. And you have, when you look in there and you realize that you probably have 3, and you talk to the man who gave you the 3 and the 4, and he says, maybe I can get you another 6. So you realize that you're going to have at most 10 pieces of wood. You want to make enough tables and chairs where you have to allot 2 pieces of the wood to the table and 3 pieces to the chairs, or whatever I'd said, but you only have at most, meaning that you can have used up 10, but you can use less than 10 pieces. So see how I've translated that word sentence into an expression or an inequation. So you take the wording of the problem and you translate them into mathematical expressions in which the variables that you use to represent the items that you want to build is no more than to the first power. Hence the word linear. So you will end up with a series of graphs that only have straight lines on it. Good? Now, what I've said so far, does anyone have any questions? Are you following? Are you understanding even intuitively? Because if you don't get that intuitive understanding, you're going to struggle with approaching the question. So speak quickly, class. Are you following or do you have questions? I'm not hearing anyone.
Following, Miss.
Great, good. Now, so your inability to solve the questions depend on you being able to represent your information graphically. If the person was considering building bed, tables, chairs, whatnot, and everything, those are many different things the man would have to process. We are two-dimensional creatures. We can only graph by hand stuff in 2 dimensions. Once it go over 2, we need a computer to help us. So we focus here on just 2 dimensions where you can get an intuitive understanding of how to do it. So we're going to only focus on 2 of the items he can build. So then, he needs to translate all those thoughts to something he can work out, to expressions he can work out, or equations or inequations that he can work on. Now, notice I keep saying equations or inequations. Inequations are where you have less than or equal to, greater than or equal to, greater than or less than symbols separating terms on both sides, left side and right side of those expressions. If it's an equality, we call that an equation. If it is not an equality, we call it an inequation. Now, we need to know how to show on a graph an equation or an inequation. We all know how to show an equation. We draw a straight line, and the line is the equation. But what if we have to show an inequation? How do we show it? You learned that in mathematics at grade 8. I know because I used to teach it. So the question is, how do I show an inequation? That's between grade 8 and grade 9. How do I show an inequation on a graph? And just a reminder of how to show an equation. So I'm just going to go back through what was done so that everyone can be on the same page, especially for those persons who were expressing that they didn't quite understand. So 4x1 plus 2x2 equals 16. You're used to getting maybe 4x plus 3y equals 16. In linear programming, we only use x. We use x1, x2, x3, x4, x5 to xn. So you don't use x and y, you only use x. And the 1 and the 2 are subscripts. So it's not a superscript. It's not written to the top. It's written to the bottom. So it's x1, x2, x3, etc., etc. So always remember that. Now, so 4x1 plus 2x2 equals 16. Graph that for me. So instruction is graph that equation. So you furrow your brow and you say, but miss, how do I do that? You never gave me any coordinates. You must get your coordinates yourself. How do I get my coordinates? 0 is your friend. You cannot solve an equation with more than one unknown. So it means that you must eliminate one of the unknown and solve what remains. So you says then, let x1 be 0. Right away, x1 is eliminated. So you have 4 times 0 plus 2x2 equals 16. If you eliminate one of the variables, then you can find a value for the remaining variable. So now you have 2x2 equals 16. Voila, I can see that the value for x2 is 8. But you need, so you have a coordinate here that where x1 is 0, x2 is 8. You have one coordinate, a pair of coordinates, but you know to graph a straight line, you need a minimum of 2 points. So you need another coordinate, another pair of coordinates. So you find the value for the other value, the one that you made 0. So it means now you must make the one that you solve for 0 in this time around. So if x2 is 0, you now have 4x1 plus 2 times 0 equals 16. Aha! I can now find a value for x1. So x1 is equal to 4. So now my next pair of coordinates, when x1 is 4, x2 is 0. There you now have what it takes to graph this equation, 4x1 plus 2x2 equals 16. Good? So now turn in the page. So you know you have coordinates are 0 and 8 and 4 and 0. So you can now use those coordinates to graph this equation. So you go ahead, you draw up your axes. Now x1 being mentioned first goes on the horizontal axis, and x2 being mentioned last goes on the vertical axis. Good. So now this is your x1, your x2, x1, x2. So x1, 0 over here and 4 over here. You scale that axis up to 4. The x2, 8 over here and 0 over here means you must scale that axis up to 8. And I'm just using 1 because the numbers are small. 1, 2, 3, 4, 5, 6, 7, 8. So now you can graph your 2 lines. When x1, your 2 coordinates rather, when x1 is 0, x2 is 8. Here is that coordinate right here. When x1 is 4, x2 is 0. Here is that point right here. You take your nice straight edge and you draw a nice straight line. This line is, what's the equation again? 4x1 plus 2x2 equals 16. 4x1 plus 2x2 equals 16. Only the line is equivalent to 4x1 plus 2x2 equals 16. What does Miss Hewitt means? It means that if I put a dot on anywhere on this line and find what the coordinates are for this dot, whatever the coordinates are that I read off of the line for x1 and x2, and I plug it into this equation, my answer will always be 16. Anywhere along the line that you see a dot being put, any point, only on the line. When I pick up the coordinates for any of the points that you mark on that mustard color line and place them in that equation, will you get 16? If you take a point, mark X or with the asterisk below it, or if you take a point, mark with the asterisk above it, and you find the coordinates for that point for each of those and put them, you will not get 16. You will either get greater than 16 or less than 16. So only on the line will the coordinates that you pick up make the equation true, meaning when you multiply whatever value for x1 you pick up and whatever value for x2 you pick up and substitute respectively in the equation, you will get 16. Anywhere else, the equation will not be true. Therefore, it is only the line that represents the equal to 16. Tell me if that is clear. Quickly, class.
Yes, miss, it's clear.
Good. No, but there's a problem. It is not only equal to 16 we want to know. We want to know what if it is just less than 16. So we want to know if it is that we have an inequation that says 4x1 plus 2x2 is less than 16. Less than 16 can mean what? Tell me what less than 16 can mean. We need combinations of x1 and x2 to make this inequation less than 16. What does that mean? Less than 16 can be what number? David Gordon, less than 16 can mean what number?
15, miss.
15. Jamie Williams, less than 16 can mean what?
Less than 16 is like 15.9999999.
15.999. Tashik, what can less than 16 mean?
Any number below 16.
Any number below 16, and that is closes the argument. Any number below 16. So the question is, where do I look for any number below 16? We are dealing with what we call the Cartesian plane. The surface is a flat surface. When you were learning that, your teacher will tell you, look at your book top or the desk or the floor. That's a plane, a Cartesian plane. It's a plane because you have two dimensions, length and width. Good? So you're dealing with the Cartesian plane that is covered in infinite number of coordinate points. So if I put a dot here, I can put many dots around that. And that would be a point because it's a plane. So anywhere then on the plane, you can put a dot at a particular point. You can find coordinates that will make this equation written in green true. So then, how do I show that on the graph? How do I show the area that satisfies that inequation? We just said the mustard color line or the whatever you want, pumpkin color line. Any point on the pumpkin color line will satisfy the equation if it is equal to. So we just draw the line and say, yeah, there, I just show you where equal to lies. But when it is less than 16, it is any number below 16. How are you going to show a place or a space or a point or a set of point that can satisfy anything less than 16? Well, that has to be a space in the Cartesian plane. How do you show the space? Well, To show it, you have to identify it first. So if you know where equal to 16 lies, then it's just a matter of figuring out where is less than 16 line relative to that, and where is greater than 16 line relative to that. If the line is 16, imagine it is a number line. If the line is 6 there, that's a number line. 16 is there. Where would, let me see, left, where would less than 16 lie? To the left or to the right of 16? Go back to your number line. To the left or to the right of 16?
To the left, Miss.
To the left. So if you want to show combinations of x1 and x2 that will give you any number less than 16, you would have to look to the left of where 16 is, 16 being the dividing line or the fence line. So it is all the space that is to the left of 16. Now, you can indicate that it is the space you are after by one of two conventions. You can shade it. There, grass is growing in it. All the space, put dots or shade it or however you want to do it. Or you put strokes. You can say all of that green part. Even go out to the space, because remember, you divide the Cartesian plane into 4 quadrants, but I only have one. I'll explain why I only draw one quadrant there in a minute. So all the space to the left of the 16, 16 being the dividing line, it has to be all of that space. And I'm supposed to cover it in green spots. That is one way to show it. But because of what you're going to be after, I advise you not to show it that way. So I'm going to advise you to show your required answer this way. We are after all the space that shows us where less than 16 lie. Not for the sake of showing, but because you want to use it to do something. So imagine it's a plot of land. You want it to build your house. You have identified it. You go to NHT and you get your money and you're going to build. You separate your land from your neighbors and you say, this is your land. The space that you want to build your house, what will you do with that space? Suppose it's covered up in grass and trees. You identify the space. What do you want to do with that space? You want to leave it in grass and tree? What do you want to do with it?
Cut it down, Miss.
You want to cut it down and clear the space to build your house. Isn't that so? So on your land, you have identified your house spot. Imagine that the place that you're after on the graph is your house spot. So you want to leave it clear. So you will instead leave the other spaces that you don't need to grow up in grass. Do you see what I've done?
Yes, miss.
Good. So the place that I need, I leave it unshaded, and I shade the place that I do not need. So I've cleared out my house spot, but I left the other piece of my land to have the grass and the trees. Think about it that way. So when you give me this now, and I ask you to show me where the spaces on the graph that or the area on the graph that satisfy the inequation of 4x1 plus 2x2 less than 16, and you present me with this, then I give you a tick there. I've ticked in the part that is your answer to the question. Now, we call the space that is the answer to the question a particular set of words. We call it the feasible region or your house spot. So think of the feasible region as your house spot. Father has gifted you with a piece of land and you want to clear it to build your house. Your feasible region is similar to your house spot. So you're going to clear it out and show that that is where you're going to build your dream house. You're not going to chop down all of the land because you want to be environmentally friendly. You want some foliage to make the house, you know, looks nice and to have some cool breeze and get you some rainfall and birds chirping in there and so on. You're not going to chop down all of the land, just the house spot. You're going to leave some foliage on the land because it serves its own environmental purpose. Keep the soil from washing away, etc. Right? So you have shown us the part that satisfies the inequation and shade the part that is not a part that satisfies the inequation. Good? Now, what if, so this, let me write this over here. 4x1 plus 2x2 is less than 16. Let me erase over here because I want to show them on the same page. Suppose now I say to you, show me where 4x1 suppose I say show me where 4x1 plus 2x2 is greater than 16. Now the numbers sound familiar. X1, X2, you have you 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. It's my stomach growling. I'm hungry. You draw your line. I'm going to use a blue line. So you draw your line. Same 0, 8 and 0, 4, right? The axis. Supposed to be a nice straight line, right? So the line would be 4x1 plus 2x2 equals 16. But the instruction says show me where is greater than 16. Again, you look at your number line. 16 is the dividing fence. Left and right. Is it to the left or to the right of 16 that I'm asking you to show me? Left or right?
Right, miss.
Right, so it means that your house spot is now on the right-hand side. So you want over there to be clear. So it means that over here, so is where you're going to leave to grow up in grass because your house spot is now going to be on the right-hand side. So over the right-hand side that you have left unshaded is the answer to the question. Are we together?
Yes, miss.
Good. Suppose I insert an equal to sign. 4x1 plus 2x2 is greater than or equal to 16. How do I modify my answer? Where would I indicate is my response?
On the line, miss.
So I need both the line and the space. Isn't that right? So you indicate by not making the shadings touch the line. So you would make sure that your shadings fall below the line and don't touch the line to show that it is a part of your response. So you will shade below and not make your shading touch the line. Good. If it is that it is not a part, you must make sure you begin your shading on the line to show that you're shading out the line. That's how you modify that. Now the thing is, when you're doing a linear programming, you cannot construct different graphs for all your equations. All of them have to go on one dege graph. So if you have 4 equations to draw, they all have to go on a single graph. I remember walking through an exam one day and saw a student trying to do the problem, and you had about 4 or 5 equations, and she was drawing 4 or 5 graphs. And though I pulled the paper away so she realized that she's doing something wrong, she got very upset with me and continued on her way. And of course, you know that I just mentally gave her the 0 and walk away. All right? So don't ever make that mistake of drawing, and I've seen students do it up to the last exam cycle. Do not draw your equations to represent your graphs on different graph paper. You will never be able to solve the problem. They must all go on the same graph. Why? Because you're looking for a region that is common to them all. You're looking for a feasible region that is common to all your constraints. Why? Because it's when you find a common area among or between all your constraints that you can properly allocate your resources to satisfy those constraints while seeking to achieve your objective in the best possible way that you can. So you can't take a plane to go to Europe if you don't look at the vacation time you have, the amount of money that you have, and the expense that you're going to incur when you go there. You have to first consider, do I have any vacation time? Do I have the money? And does my money, can my money satisfy the expenses? When you have done that, then you'll book a hotel that satisfy all those other constraints. So you have to solve the problem with all your constraints in mind at the same time. That's pretty much what you're doing. I'm solving the problem by looking at all my constraints at the same time, and I can only come up with a proper solution to the problem that fit the constraints that I am experiencing. Tell me if that makes sense quickly.
Yes, miss.
Good. So I'm going to demonstrate with 2 questions on the paper for you.
But miss, for the 5, we have the same answers, miss, it's just that you did a more detailed working. And I was
Yes.
also confused because all of them is the same 4 to 116, so I wasn't sure if I should do them on the same
No,
graph.
the way that the question is posed, it is required that you do them on the different graph, because notice they're labeled A, B, C, D, E, which means that
Yes,
they
miss.
must go on different graph. So I'm not saying you did wrong. I'm just demonstrating for students who indicated in the chat that they didn't understand.
Okay, miss.
All right, good. So we're going to go to a question to apply all of this now. Share your tutorial sheet with me, please, quickly. Oh, my stomach is.
Mr. Sharing.
Oh, sorry, I need to stop sharing, right? Go ahead. Good. Scroll down a little bit for me, Abigail. Scroll down. Down, down, down. Go back up a little bit, Abigail. All right. Let me see. Go back down to 13. Let me see 13. All right, we're going to look at 13. Here's how I'm going to look at 13, because it has multiple It has multiple requirements. It says you're minimizing costs. Remember I said that you need to have your objective begin with either minimum or maximum. It's subject to the constraints of 3x2 greater than 90, 8x1 plus 2x2. Is that greater than or equal to 160, 3x1 plus 2x2 greater than or equal to 120, x2 less than or equal to 70, and x1 and x2 greater than or equal to 0. So is this greater than or equal to? Is there an equal to or less than or equal to? There's a blue line there, so I'm not seeing if the equal to sign is underneath it. Is that greater than or equal to? Greater than or equal to?
Yes, miss.
All right, great.
Yes, miss.
Thank you. Class might run a little bit over time today, and we're gonna have to have a makeup time on the weekend, so guys need to tell me when on the weekend. All right. So 1x1 plus 2x2. Now, all of these must go on one graph. So notice you're asked to graphically illustrate the feasible region, indicate which corner points produce the optimal solution, and what is the cost of this solution. So, all right, you can stop sharing now. I'm going to take back my share. Good. Now, the objective here is to minimize the cost. This problem is what we call a formulated problem. They cut through all the words, take out the words, and made them into equations or inequations. You're going to have to know how to do that for yourself. So here we're going to begin with a problem that has been formulated for you already. So it's min. Z refers to the objective function. The two dots refer to such that. So you're going to maximize your objective function such that. That is what all of that means. See how nifty.
Minimize, miss.
Min, M-I-N, right? So you see how nifty maths can be. All of that mean minimize your objective function such that when you produce 1x at a cost of $1 and when you produce x2 at a cost of $2, you would incur minimum cost. That's all that it means. But however, you're subject to the following constraint. x1 and 3x2 is greater than or equal to 9, meaning that the minimum requirement that you have for the first constraint is 9. Whether it didn't tell us what it is, if it's 9 hours, $9, 9 square foot, that's not important, right? So to produce 1x1, you need 1 unit of whatever the constraint is, and to produce an x2, you need 3 units of whatever the constraint element is, but in total, you have at least 9 units of it. That's how you read that. 8x1 and 2x2 is greater than or equal to 160. Again, it means that whatever the resource constraint is, you have a minimum of 160 of it. You can find 160, 161 up to however many you need. You distribute that resource.
Miss.
Yeah. I'm listening.
Isn't the first one 90 and not 9?
Oh, 90. There you go. Thank you.
Yes, miss.
Mm-hmm. So for the second constraint, you have at least 160 of it. To produce an x1, you need 8 units of it. And to produce an x2, you need 2 units of it. So together, when you produce x1 and x2 in the appropriate ratio, you will need a minimum of 160, or you may need more. That's how you read that. 3x1 plus 2x2 is greater than or equal to 120. Again, it is some constraint. They didn't specify. But it means that when you produce an X1, you're going to need 3 units to produce the